Okay, so we're looking at oscillating systems. The next thing we need to look at was energy exchange for a pendulum. So we talked about energy trades back and forth between kinetic energy and potential energy in a spring. Now it's for a pendulum. So for a pendulum, we switch from translational to rotational kinetic energy because the pendulum rotates. And we switch from spring potential energy. Obviously, there's going to be no spring involved. It's going to be gravitational. So let's start. If I have a pendulum of any kind, here's going to be my pivot. And this is, of course, the equilibrium. That's where a pendulum hangs vertically. Let me not draw the whole pendulum. Let me just draw its center of mass. So the center of mass might be here to start with. But then, as the pendulum swings, notice that the center of mass will fall. In fact, the center of mass is going to reach its lowest point at the bottom of the swing. So no wonder it's going the fastest there, because that's where it's got the lowest potential energy. We usually set h equals 0 down here. So h equals 0 represents the lowest height the center of mass gets to. So our gravitational potential energy is just going to be good old mgh, where h is the center of mass height. And that's kind of it. You already knew the formula, mgh. Now it's just, that's where the pendulum, how the pendulum goes faster. It goes faster when it's lower. It gives up potential energy for kinetic energy. A pendulum speeds up, it goes as it goes towards equilibrium. The same reason why a ball falls down, it speeds up, because it gives up gravitational potential energy. It might be swinging along this arc, right? A pendulum is attached to a pivot, so it's constrained to move along an arc, but it speeds up for the same reason, okay? Because it gives up gravitational potential energy. Now, I should mention that sometimes you don't want to track a pendulum by height. You don't want to track its center of mass by height. A lot of times for a pendulum, we want to talk about angle. So there's a relationship between these. For instance, when the center of mass is over here, the pendulum is that angle from the equilibrium. So let's see if we can find a relationship between h com and theta, which there obviously is one, because when the height is 0, what's the angle? 0. And the larger the angle, the larger the height, right? There's obviously some relationship between those two, and it's just purely geometric, okay? So let me show you what it is. So this distance I'm going to write as d com. It's the distance from the pivot to the center of mass of the pendulum. Now, our pendulum is some kind of rigid body, so of course this is d com as well. If I haven't drawn it that way, that's just my poor drawing, right? The center of mass will not change how far it is from the pivot, right? It's just where, you know, if it's below it or not, or off to the side. So this is the same length, right? This is supposed to be a circle. I think it got a little wonky. I didn't quite draw it, but it's supposed to be a circle, right? So here I go. I'm going to drop a line here like this, so that this is a right angle. And I want to point out that just this part can be expressed using that right triangle as d com times what? Cosine of theta. And I want to also mark off this. What's that distance? h com. It's how high the center of mass is above the bottom. Look at what these two distances add to. Hcom plus dcom cos theta adds up to dcom. So that's just a smidge of geometry. Okay, so Hcom plus dcom cos theta equals dcom. So let me solve here. This is my relationship. If you ever want to go back and forth between these two things, what angle does the pendulum make with the vertical, and what height is the center of mass above the ground, or above the bottom of the swing? That's your formula. That's our relationship between these two. And the only extra ingredient you need is how far is the center of mass from the pivot. So that formula is your friend. So to summarize, the potential energy is mg Hcom. That's if you have someone's nice enough to tell you how high is the center of mass above the vertically, above the bottom of the swing, but maybe somebody is going to ask you in terms of the angle. So they don't tell you how high the center of mass starts above the bottom of the swing, they tell you the angle that the pendulum starts at, then you can use that. Okay? And then of course, let me remind you what the formula is for rotational kinetic energy. So then you do your standard energy conservation, right? So you would do these two initially equals those two finally, and do your kind of standard energy conservation stuff. Are there any questions so far? So again, if the geometry didn't quite click, this formula is available for you, so you don't have to memorize it. It's on the equation sheet. I can't remember if it's exactly in that form or not, because for us, most of the time we'll focus on the simplest pendulum possible, which is just the kind you looked at in lab. So I'm going to immediately show you what happens if we go to a pendulum that's not some bizarre shape, but in fact is nice. So right now, this pendulum could be shaped like anything. I didn't even draw it. This pendulum could be shaped like this. You can make a pendulum out of anything, right? All you have to do is you have to attach it to a pivot. So it could be some blob thing going back and forth, okay? That's, by the way, known as a physical pendulum. So a physical pendulum is just some general shape. For instance, if you get on the monkey bars and swing back and forth, you are a physical pendulum. Obviously, you are not a point mass. But let's focus in on what's called a simple pendulum, which is the kind you looked at in lab. Which just looks like this. This is called a simple pendulum. Now, when I say simple, that's not the same as the simple and simple harmonic motion. I haven't yet told you what that's all about. All of the things we're looking at are simple harmonic motion, but this is, when I say simple pendulum, I just literally mean the simplest pendulum possible. So it's a point mass m on the end of a string of length L, which has no mass of its own. So if that is the case, where is the center of mass of a simple pendulum? At the very end. That's the only place there is mass, right? So if that's the case, how far is the center of mass of this pendulum from the pivot? L. So then, dcom simply goes to L. And I think that's the form that you might see this equation on the formula sheet. It doesn't have dcom in it, it has L in it. That's because it's a simple pendulum. And I'll show you another trick that's your friend when you are working with a simple pendulum. Let's see what becomes of the kinetic energy term. 1/2 I omega squared. Does anyone remember the rotational inertia of a point mass? mR squared. Good. Because you need to know that for this week, right? Yes. It's a point mass. And then what do we use for R? L, right? R equals L. R is the distance from how far that mass is from the pivot. In this case, it's L, right? And then, as far as the omega, of course, that represents at any given moment what's the angular speed of the pendulum. But I might want to talk about what's the linear speed of the actual pendulum bob, because that's the only place where there is anything actually is. So then we'd use V equals R omega, right? What's the R?
Radius, L.
L. So I can plug in here, omega is V over L. And let's see what we get here. If I simplify this, I get 1/2 mv squared. So when it's a simple pendulum, you don't have to use rotational kinetic energy. You could instead use translational kinetic energy, and the result would be the same. If you remember, you actually did a problem with a pendulum before we ever got to this unit. If you go to homework, what was the energy homework? Homework 7? Sounds right? Okay, I think whatever was the big energy homework, right? You did a problem where a child was on a swing set and swinging up to the top of the thing, right? Top of the trajectory. You didn't need to know about rotational kinetic energy. You just use this. Well, the reason why is that if you have mass only in a single point, that's what a point mass is. If you have mass only at a single location, you get to choose. Do you want to think of it as having a linear motion through space that just happens to be a circle? Or do you want to think of it as this system rotating in place? You get the same answer either way. You get the same equation. The only place you can go wrong, of course, is accidentally double counting. You can think of it as a rotational system or as a translational system, but not both. Okay? So for a simple pendulum, your kinetic energy is going to be 1/2 mv squared. That would come out of thinking of it as translational or thinking of it as rotational. That's the result either way. And then, of course, what you did in your homework problem before, you just thought you didn't have options at that point, right? You had to think of it as translational. But it's nice to see that if we think of it as rotational, then it comes out the same either way. And then, of course, the other thing you did in your homework with that child in a swing problem was use that. And, of course, we used MGH. Of course, I did not ask you for the final angle, right? Because I just showed you the geometric relationship between height and angle. You didn't have it at the time. So I think in that problem, it gave you the initial speed and asked you for the final height, right? Something like that. So a few bells and whistles aside, this is kind of old news, right? So the only thing I've really shown you today is that you don't have to talk in terms of height, you can talk in terms of angle. And then for the simple pendulum, you have choices on whether to think of it as rotational or translational. Either way, you get 1/2 mv squared. Of course, it's important to use this form if you have mass at more than one location. For instance, if you had something like this, like a pendulum made out of this, there the whole notion of V doesn't make any sense because this end is going the fastest, this is going slower, this is going slower, and there's no speed at the pivot, right? So there is no more just V of the pendulum. What the pendulum does have at any given moment is a common omega. That's the whole reason why we introduce these angular variables, is because we can say that an object has them in common, right? We talked about a record spinning, right? A record spinning, different points have different v, right? Or we talked about a carousel, right? The big kids on the outside have a faster v. The little kids on the inside have a slower v. But they all have a common omega. So for something like this, you're not going to get a whole lot of use out of this, okay? That doesn't make sense. If you want to take this to be the total mass, well, there's no common v for the whole object. So then you have to use this one, right? But a simple pendulum, you kind of can do it either way, because a simple pendulum happens to have mass in only one spot. Okay. Okay. Have any questions on the energy before I move on to the timing, the period of these systems? Okay, so let's do that. So this is the third bullet point I mentioned in these systems. So remember what we did. We talked about kinematics first. We did a play-by-play to understand how oscillation arises in the first place. But it had to be concepts only because the acceleration is not constant. So the constant acceleration equations go out the window. Then we went and we did energy. Energy is great because it can do complicated motions where the acceleration is not constant. But the one drawback is that it doesn't do time. So now, in these kind of systems, we really want to know how long does it take to oscillate. So we're kind of stuck, and this is where I'm just going to pull some results from more advanced courses. So what is the period in these systems? So we're again looking for the time it takes to oscillate once, but the acceleration is not constant. So these are just going to kind of be pulled out of a hat. So the spring force law we mentioned was this. And it turns out that if you take some advanced math, this is like beyond calculus. This is something that I think it's math 275. It's really high up. To be able to show that the period of this system, based on this force profile, which by the way causes the acceleration, right? The period formula is equal to this. So I guess I can put advanced math. Notice that the answer has a pi in it. Where did the pi come from? There's no circular motion. It's just something bouncing back and forth on a spring and on a line. Don't worry about it. Okay? But I do want to, since this is completely just out of the hat, I do want to point out the proportionalities and how they make sense. First of all, according to this, if the mass that is bouncing on the spring is larger, what does that do to the period? It's longer. Makes sense, right? If you have more mass, you have more inertia. You're more stubborn to changes, so you're not going to want to go with the spring. So more inertia in the object that you're dragging around, so it takes longer to complete a period. The spring has a harder time dragging you around. If you increase the spring constant, what does that do to the period? It decreases, because it's the denominator, right? Don't let the square root throw you off. You make the number bigger in the denominator, it's going to divide by a larger number, it's going to get smaller. Now, a spring constant, this means that the spring is more stiff, right? It's a more stiff spring, and a more stiff spring is going to cause you to oscillate quicker. Right? If it's more stiff, it means it exerts more force at any given displacement, so the time is shorter. Now, what's as important to this formula as what's in it is what is not in it. In fact, it's probably more important to realize that there's something big that's missing, and that is the amplitude. Remember we said amplitude was the maximum distance of release. So it's how far it ever gets from equilibrium. Now this is not a property of the system. These are inherent system parameters, right? So you look at the system, it has a certain amount of mass attached to a certain spring. But this is initial condition related. How do you release it? Do you release it from a small amplitude or a large amplitude? And this formula claims that where you release it does not matter. So it's saying that if I had two identical systems, right? Exact same mass, exact same spring, and I pull one back like this, and I pull one back way further, and I release them, same period. Okay? The details of how you choose to release it will not affect the period. The only things that affect the period are things that are inherent to the system. If you see that mass and spring system sitting there, no oscillation, it's just in equilibrium, not doing anything, you can say, I know what period that system's going to have. Because you don't need to specify how you start it. Any oscillation you start there is going to have the same period, because the period depends only on things that are inherent to the system, not on the particulars of how you release it. And that is what puts the simple in simple harmonic motion. Okay? Harmonic motion is oscillatory motion, but what would be a simple versus non-simple? Well, simple harmonic motion is oscillation where the oscillation is going to be determined by what the system is like, not on the particulars of how you release it. So the period depends on inherent properties of the system, not on the particulars of how it's set in motion. Okay? That is what puts the simple in simple harmonic motion. We like to look at these kind of systems because then we know that their period of oscillation is going to be determined only by things that we can't help. Okay? Now it doesn't turn out that doesn't always happen. It turns out that it only happens for one special case. Only if the restoring force, which in this case is the spring force, is directly proportional to the displacement from equilibrium. That is the only case where it happens. Now, we can think about conceptually why that is. If we pull two identical systems back, one back this far, one back this far, how could this one that has so much further to go, how could that make it up for it and oscillate in the same time? How does the one that has much further to go, how does that still have the same period? It's faster. Why? How does it go faster? It's the same spring, right? Same K. But you pull it back further, and what happens to the spring force? It's larger. So what happens is that if you pull one back like this and pull back one much further, this one's going to have more force, right? And it's going to get accelerated harder. And it turns out that it can exactly make up for the fact that it has longer distance to go by the fact that it's going to do it faster. If you have exactly this force profile, you will find that the period depends only on inherent system properties. If the spring force was not that strong, right, if it did not grow, linearly with distance, maybe it didn't grow quite as fast, then the one that would fall further behind, the one that had further to go, would fall further behind. It would take longer to complete its period. And likewise, if the force grew faster than this, say if the force grew as the square of the displacement, it turns out that then it would be overcompensated, and the one that would have a larger oscillation would go quicker, right? So it turns out that this is the Goldilocks situation. When the restoring force is directly proportional to displacement, the fact that one has a longer distance to go is exactly compensated for by the fact that it experiences just the right amount of force so that they can oscillate the same period. Okay? Have any questions on that? Yeah?
When is the restoring force not going to be proportional to the displacement?
In the case of the spring system, it definitely always is. So we're lucky that that system has that feature. The pendulum, it's not. So pendulum is not really this type of system. We approximated that it is, but it's not really. Let me show you. For a pendulum, let's say take a pendulum here. We have gravitational force. That is the source of its restoring agent, right? That's the thing that wants to bring it back to equilibrium if it's not already there. So let's calculate here. My torque, let's say, well, this should have really been the center of mass. I want to make sure that I'm doing this as generically as I can. So there's the center of mass of the pendulum. That may not necessarily be the end of the pendulum, but that's where the center of mass is. That's where the force of gravity pulls. Okay, so let's calculate the torque, RF sine theta. R is, and this is something, again, you definitely want to know for this week. R is what distance from the center of mass to the pivot, right? So R is generically, it's leverage, right? It's the distance from the pivot to where the force is applied. In this case, it's the center of mass. So we've been calling that decom today. mg is, of course, the force. And then the theta, the way you get that is you draw a dotted line out from the pivot through where the force is applied. You measure that angle. You measure the angle between the radial line and the force vector, right? So that'll be my theta. You guys remember this?
Yes.
Okay. That theta is, by the way, very conveniently, that theta. So that's going to be cool. That's actually the angle from equilibrium. I guess I'll call it theta EQ just for purposes of symmetry. So let me copy that over here. Instead of the force of the spring bringing it back, the torque of gravity is what's bringing it back. I have decom times mg times sine of theta from equilibrium. And of course, something else you should know for this week, the net torque causes what? If you apply a net torque to an object, it will do what? Homework 9 that you just finished? Angularly accelerate. And what's the rest? What's the final ingredient? What is it? Yeah, there it is. Okay. So let's do a play-by-play. Let's compare these two formulas. It's looking pretty similar, right? Mass goes to its rotational analog, I, right? A goes to alpha. Instead of a restoring force from a spring, it's a restoring torque from gravity. I have the displacement from equilibrium, angular displacement from equilibrium. I have the spring constant, which is some property of the spring that doesn't change. And I have some other constants here that are also not going to change, right? What's the one thing that prevents me from making this a perfect analogy? The sign. So let's ignore it. This is the kind of thing that drives mathematicians crazy. How can you do that? Well, you can do that by realizing that sine has a very special property. For small angles, the sine of theta is approximately equal to theta. Now there's mathematical reasons for that, but as proof, try plugging in a really small number in your calculator, hit the sine button, you'll get back almost the same thing. Okay? So if we restrict our attention to small angles, then we can ignore the fact that this system isn't really simple harmonic motion. Okay? Because remember, in order to have truly simple harmonic motion, you need that the restoring force is directly proportional to the displacement, not proportional to the sign of the displacement. Okay? So do you remember in lab when I said, or your instructor said, hey, when you're doing the pendulum system, keep the angle really small. It's not going to work. Well, that wasn't for the purposes of experimental error, like from air resistance or something like that. It's because if you don't keep the angle small, then what angle you release it from actually affects the period. Okay? So it's not really truly a simple harmonic motion system. It's just one that if you go to small angles, it starts to very highly approximate one. Okay? So let's write down our equation. T equals, now if I had to pull the first one out of the hat, we shouldn't have to do it here because I can replace everything with the comparison. So the m now becomes what? I. So if we think of it just like a change of variables, right? So what we were doing before, it's now just we changed all the letters. So m changed to I. And what was the equivalent of k? Decom mg. So my analogy is this, okay? That's the formula for the period of a pendulum. And what it depends on, again, it's more important what it doesn't depend on. It doesn't depend on the angle of release, which is the initial conditions, but that's only if the angle is small. Okay? Because it really actually does depend on the angle. We just pretend that it doesn't for expediency. So if in lab you did not keep the angle small, you probably found you had a horrible percent error. And it's not because you did something wrong, it's because this formula doesn't even claim to be correct anymore. So you're comparing your experimental data against a formula that doesn't claim to be valid. Now you might say, how small is small enough? Well, that's a matter of personal taste. If you want this formula to only produce like 1% error, you better keep it real small. If you're okay with 5% error, make the angle a little bigger. If you're okay with 57% error, and I can't imagine why you would be okay with that, go ahead and swing it like this, okay? Swing it at a 90-degree angle. So, point being is that there's no magic cutoff, but this formula is really only even reasonably accurate for small angles, okay? For our purposes in this course, you can always assume that's the case. So if you're doing your homework and you need to find the period of a pendulum, then you can use this. The other thing I want to point out, the formula also doesn't depend on mass. Now you might say, what do you mean? Mass is right there. It's in the denominator. Well, remember, there's always going to be a mass in the rotational inertia too. So dividing by the mass will actually get rid of it. Now the reason why mass doesn't matter is because what is driving this oscillation is gravity. And we of course know that gravity will pull on things harder just because they're more massive. So that's why it makes everything accelerate the same, right? So unlike the spring force, right? Spring force will not change how much it pulls just because you have a larger mass. This, the force of gravity will increase if the mass is increased. So therefore, the mass won't matter. So there is our pendulum formula, and now I just want to use it to close out the unit. Let me show you a couple uses of it. Are there any questions before I clear some space? Okay, so let me now use this. One type of pendulum that you might be interested in is a solid bar like that. Let's say it's a solid bar of mass m and length L. So we have to decide what to use for decom and for I. So what should we use for decom? What is it?
L.
L is the distance from the pivot to the center of mass. Half L, right? The center of mass of a solid bar is going to be in the middle. Does anyone remember, maybe you spun your wheels a little bit on the revolving door problem of homework number 9. Does anyone remember what the rotational inertia is of the panel like this, rotated about the edge? Not 1/2. 1/3. Now you don't have to have that memorized. I just thought maybe you might remember doing that problem, but it is on the equation sheet. All right, so let's use that to calculate the period of that system. So we'll throw it in. T equals 2 pi square root of 1/3 ml squared over L over 2 mg. The mass cancels as advertised, right? And we have an L that cancels as well a little bit, and we get 2 pi square root of 2/3 L over G. That's the period of such a pendulum. And notice that really the only active ingredient is length. So the length will determine the period. As long as it's shaped like that, the only thing that will affect the period is how long that bar is. The longer it is, the larger the period. One of the systems that you might want to use this for, here's your leg. You walk around on 2 pendulums like this. I'm walking around on 2 pendulums like this right now, basically. Obviously, the mass distribution in my leg is not uniform from thigh to foot, but it's close enough, right? It turns out you can measure your leg, okay? Put it into that formula, get the period. And of course, the period will be going from here to here. That's half a period, right? Because this to this to this would be a whole cycle, right? So half a period would be like this. And you can calculate, based on how far you step, you can calculate your distance of 1 step divided by the time, which is half a period. You can get an average person's walking pace like this. Basically, right, you're not running or anything, you're just strolling along, minimum energy, right? So you're just letting your legs swing down, right? Just letting gravity do the work. You can estimate a person's average walking pace by thinking of them as walking around onto a pendulum like this. Let's do the one you did in lab. That was the simple pendulum, just the simplest pendulum possible. Also of mass m, but now all the mass is on the end. What do we use for decom now? L. Now the mass is all on the end. That's the center of mass. And the rotational inertia again is
mr squared.
mr squared, or in this case, r is L, right? Let's plug that in. So we'll put in our rotational inertia, ml squared. We'll put in the new decom. And cancels again as advertised. And now I get this formula. Looks very similar with the absence of the factor of 2/3. That, by the way, is also available for you in the equation sheet. You just want to jump and use that if you have a simple pendulum. Once again, the longer the pendulum is, the larger the period. So you guys explored this in class, right, or in lab. It's rather than making the pendulum longer and observing that the period was longer, it's just annoying to have to to attach a progressive longer rope. Instead, you started off with the longer pendulums and then got shorter, right? By tying up the string. You remember this? Okay. Now, the relationship between period and length of pendulum is like that. And so you guys use some trickery, right, to make it linear, right? You squared both sides, right? So if you square both sides, you get t squared equals 4 pi squared over g times L squared. No, L, just L. Yep. You remember this? Yes. Okay. So what you did was, you guys, in order to prove this theory, you plotted t squared versus L. You hopefully got something linear, and you hopefully got something where the slope of your data was 4 pi squared over g. Remember this? That was how you confirmed this equation. You varied the length of the pendulum, and then you saw its effect on the period, and then you checked if it met the theoretical prediction. I guess the other thing I could mention, if the lengths were the same, which pendulum actually has a longer period? The second one, yeah. This has a 2/3, and you square root it, it doesn't make it bigger than 1 sudden. So I guess I'll call this pendulum, I'll call this my physical pendulum, I'll call this my simple pendulum. The period of my simple pendulum is greater than the period of my physical pendulum if they have the same length. It takes longer to oscillate my simple pendulum. Now, the reason why that is something that is very tied into something you should know for the exam, because it was on homework 9. Why do you think it takes longer to oscillate the simple pendulum? Mass distribution, right? The mass is further from the pivot. It's harder for gravity to take this around. Here, the mass is uniformly distributed from pivot to edge. Here, it's all on the edge. So we talked about that factor in many applications, and here it is again, right? The rotational inertia here was ml squared, but here it was only 1/3 ml squared because the mass is closer in. So that's the simple harmonic motion unit. Know the concepts of the kinematics, know how to compute energy exchange, Ke and Pe, and the formulas to compute the period. And realize, most importantly about those formulas about the period, is that they are dependent only on inherent system parameters, not on the particulars of how you set the system into motion. And for a pendulum, that's actually only true for very small angles. So our pendulums are always going to have small oscillations. Okay, any questions? Okay, so I think I'm going to knock off early today because I think I've gone over a few times recently. That closes out the simple harmonic motion unit. That also closes out homework number 10. We'll start fluids.